Good evening, everyone. This is Van Liang from home. I hope you all had a wonderful Thanksgiving holiday. Tonight, we're gonna do a quick video session of the last lecture for the control part. So here we are. Let me get started. Let's just quickly review what we have done in the first two lectures, or I would say 1.5. So essentially, last time we look at the cruise controller design. After we introduced the basic concepts for control in the first lecture. Okay, for this cruise controller design, we came up with models and inputs for the dynamics of the car. And we tried the first model, which is x dot equals 3 divided by m times u. Here, m is the mass, u is the input, which actually kind of model the how hard you press on the gas pedal or the brake. Okay, x is the state variable here, which is in this case is velocity of the car. So we tried the first attempt. You see, we're gonna set the input where the error, which is the difference between the target speed and the state variable, which is the real velocity of the car. Whenever this guy is bigger than 0, we're gonna have u set at a constant value, which we denote as u max, which is maximum gas pedal pressing you can get, or the maximum brake you can get. Or when the error is smaller than 0, we're gonna put it on the other side. And if when the speed of the car reaches the reference value, we're gonna say, okay, there's no input. And we discussed this. We commented that actually this model on paper works, but in reality, the fast switching switching of this gas pedal and brake is gonna be not good for the car. So this design is not good. Now the second model we said we're gonna model have a better model, use the proportional, we put the input, the u, proportional to the error, which is the e, which is the difference between, once again, the difference between the reference value and the real velocity of the car. And we see in this case, actually the real model for the car, there should be a resistance from the air. This one should be taken into account. So the reason, eventually the result is, if we use this proportional input, we found that actually the car does not reach the reference speed when everything kind of stabilized. Okay, and then we say the reason is because the model is wrong. Actually, we have a actually detailed procedure to calculate what speed you should be at, when you have the wrong model. Okay, so with the new model, we crack this, right? We put the resistance there. How shall we design an input signal that can learn, at least that can track the reference? But still, you need to recall that a controller should have all these following good properties, such as stability, the tracking, and robustness. Okay, so here is our third attempt. We say, okay, we have the cracked model as s dot equals c divided by m times u, then minus gamma times x. And then why don't we take add something to the proportional thing, the proportional part, right? The k times e. Then we can make sure, at when everything stabilized, we should be able to do the tracking on this, right? So if we put u equals to ke plus gamma times m divided by c, then times x, we can realize that if we set x dot equal to 0, which means, it certainly is a stable state, right? After some struggling, then we should, we solve the equation and we realize actually the state should be at s equal r, which is good, right? At least it can do the things. Now, what is the problem with this attempt? What is the problem with this attempt, right? Well, let's look at this attempt again. So our input will be k times e plus gamma times m times c divided by x. Well, by looking at this, you probably gonna realize this. The k, you can set a value, and the e can be, you can measure you have the value of the reference, and you can measure the speed at any time. But you also need to know gamma beforehand, right, which is error resistance, and you also need to know the m and the c, which is the mass of the car, and c is what we said is a lumping parameter. Lumping parameter is the electrical, mechanical, driving force of the car. When you can use this to describe, to relate the input to the related force. Actually, is I think remember it's F equals C times U. Related the force to the car from all the electromechanical driving force, right? The engine, or the brake. So then we need to know all these parameters. That's exactly the problem. This thing is good, on paper, but all of a sudden we have to know the value of various coefficients we do not typically know, and some of them actually is ever changing, right? For example, the mass of the car. When you have 1 people in the car, it's different when you have a full load. You have 4 people in the car with the garage, the trunk, filled with whatever grocery you get from Costco or whatever, right? So the problem with this model is it is not robust. Okay, it's not a robust way. And go back to attempt 2. Remember attempt 2. We have the KE, but it's not tracking the error. The next thing we can try actually is we call it the PI regulator. The P stands for proportional, and I stands for integral. So you can see you not only have the KE part here. I added some extra information there. The input can be time dependent, right? The input to the system can be time dependent. Exactly. When you can hit the press, you can hit the gas pedal. You can also hit the brake. It's changing. From as time goes by. So here literally I still have the KE part, but also I have the K times an integral of the error part. Okay, and why don't we do a more generalized thing? Include another part, which is the derivative part, the D. This is what you probably have heard a lot. People call this PID regulator or PID controller. Instead of the last term here, you have another K here, but also you have the error changing rate. Well, remember, the error is just the reference times the difference between the reference and the real speed, right? So essentially, this d dt is the dx dt pretty much, or minus dx dt, right? Depending on how you define the error. So yeah, it certainly is the rate of the velocity, okay? The changing rate of the velocity. Okay, having this, actually, we can try this again. So this is the PI. Okay, it's the PI. Regular performance. You can see that it can go to 70 miles per hour pretty much in 1 second. I think that's 1 second. So here there's a breakdown of this approach. It's certainly P, which is proportional gain. It contributes to stability and medium rate responsiveness. The I, tracking, and its job is do tracking and disturbance rejection. It's slow rate responsiveness, okay? and may cause oscillations when this gain is large. The D part is fast rate responsiveness. It's certainly sensitive to noise, because it's directly proportional to the change rate of the velocity. So when you have a noise coming in, then it's gonna be sensitive to that. Okay, it cannot be too large. I'm talking about the KD. Okay, the KD cannot be too large. If the KD is too large, then your system, it certainly is like when you have the first attempt. You're probably doing some damage to your car. Okay. All right. So PID, here is a comment, is by far the most used low-level controller. Note here, however, stability actually is not guaranteed. When you use this, it's not always guaranteed, right? When you change your KP, it's just not. You don't have to every time have a stable controller out of this game. Okay. And also, feedback has a remarkable ability to find uncertainty in model parameters. And look at this. Actually, we comment on the third attempt, right? There are too many parameters we're gonna input to the model. The C, the M, and the gamma, the error resistance, etc. Here, you see you have nothing of that. You have nothing of that. Okay, you just track your error, which is feedback, right? Feedback information, right? And also you just have three constant parameters, which you should play with it and find out a nice combination such that the whole thing is stable, it's robust, all those good properties. Okay, here is it's certainly some thought experiment. So back to the cruise controller, the P regulator. I'm still using the PID, but I'm setting, at the bottom, I'm setting the key I and key D both equal 0 and key P equals 1. That means it's literally proportional a P regulator. Okay, and you see it's stabilized for this case, for this specific case. When C really equals 1 and M equals 1, gamma equals 0.1 and R equals 1, then actually the proportional controller or the P regulator, it didn't deliver. Okay, the reference R equals 1, but this guy is stabilized at 0.5. We already commented on this before, right? So depending on your real model parameters, the specific value is stabilized is gonna change. It's gonna change. Okay. When we include the integral regulator, integral gain, then you can see in this specific case we are putting KD equals 0, but key P and equals key I equals 1, and also we still keep the former value for C, for M, for gamma, and for R. Okay, and this time the system reaches the reference value after I think 5 seconds, pretty much. It's kind of slow, right? But it does the job. So another thing is, if you increase the integral part, here I have the integral part too large. Here I have ki equal to 10, relatively is much higher than kp equal to 1, right? I keep all the rest the same as before. You can see this guy actually overshooting a couple times. This looks exactly like the buckling profile I have been playing with, right, with Amir. So we don't want this. Actually, you don't want this overshooting, because that's just undesirable, and you sometimes you overdo, and it takes time. Actually, if you check the stabilized the time needed to be stabilized, once again it's like 6 seconds. It's kind of long. Okay, well, this one we keep P and key I both at 1, and key D equals 0.1, and you can see this one actually even takes longer. It takes maybe 8 seconds for it to stabilize at 1. Okay, well, unfortunately I didn't do another try. I think if you play with these parameters, you can get it relatively faster than this. Okay. All right. So enough for plotted results. How do we get them, right? You see it looks simple, right? I mean, e here is just a function of time, and we see it's the difference between the reference value and the real state variable. In this case, the speed, right? And also we have three constants, kp, ki, kd. Okay. Once you choose the model, you don't need to change them in between. Okay. Now the question here is, how do we translate this term, including integral and derivative, into executable computer codes? Okay, because we need to write a code to implement this. Essentially, we implement this controller, or explain this scheme. Well, here I have a comment on proportional gain is easy. It's just read the sensor, right? If you read the sensor yin, it's equal to r. I think it's equal to r minus x. So then there you have it, right? And then you just multiply by kp. What about the rest? The rest, what about the integral and the derivative? How do you implement this on computer? Well, here I will comment on if you have learned computational language such as C or Fortran or even MATLAB. I mean, they have you should have experienced this or should have learned this, how to do a simple integral of a function, or how to realize the derivative of a function using on computer, using computer codes. So essentially, I'm gonna go ahead. Say the time. We start with the time derivative. Okay, derivative is essentially the derivative will be roughly equal to, or estimate. It can be estimated by taking small piece of the small time steps of this. Okay, so you have error new minus error old. Okay, if you're tracking error, and then divided by the difference, certainly the step size. Okay, this is how we do how we calculate derivative. Okay, I think you must have learned this in a calculus class. Okay, now the integral is a little bit different. So here you can see you have the integral here. Then once again, I'm gonna do small steps. Okay, and I'm gonna see from integral from 0 to t, it's certainly from here to here. Okay, I'm gonna break that apart into n steps, or I would say this, maybe let me see, maybe n plus 1 steps. It's roughly that. You have to you have to check this detail. I mean, one thing you can easily do is just have a 3 or 4 or 5, right? You can check whether it should be 4 or 5, or should be n or n plus 1. Certainly, you check that pretty quick. Now, when you do this, it certainly is e, and because it's a function of k times delta t, right? Because we are promoting k all the way from 0 to n. It's certainly you have this written out. Okay, and so we're denoting the function. E is a function of time, right? And this tau here is going to be changed between 0 to t. Okay, so at k step, this will be k times 30, and we denote that as ek. Okay, and we're gonna see, because 30 is here, is common. You can pull that out. Instead, I'm defining this big E equals to the sigma k equals 0 to all the way to n small ek. Okay, and here you have 30 times the E new, which remember we are saying that when you move one step further, this will be E new, right? It's going to be like that. Blah blah blah. You can look at that, which means the E new equals E old plus E. Okay, so this you can implement this into a computer code without much difficulty, right? because you have equal step size, and for each one you can track them. Okay. So here I have it's certainly a pretty general script. It's certainly you can implement this in Fortran, in C or C++, or in MATLAB. So certainly you read the error, and then you have your e dot, so you have the old so e old, sorry, this is the e old, um, sorry, actually, yeah, I think I'm having I should be careful. So e dot equals to e minus ode, okay, and then the big E equals to E plus E. It's only this thing is the error, the new error, just as we showed last slide, okay? And then we have the U equals Kp times E, then Kd times E dot, then Kl times it's this Ki actually, the integral, times the big E, because this big E is the integral, okay? And indeed we're doing additions to achieve integral, right? Because when you divide it into small pieces, integral becomes addition, okay, or summation. And this E dot actually is the change rate, okay, that is a rate. Okay, then we put this new E as ODE such that you can loop this, okay, you can loop this, and you can do the calculation again, okay. Note here, KD and KI now include the same time, the sample time, and must be divided and multiplied by dt respectively, okay. So KD and KI, so it's certainly because it should be KI times E times the integral, but this E here is not the whole integral. Let's go back and check, okay, because it should be KI times this whole thing, right? And right now we are time the big E, but you see here this E new and this E here, okay, sorry, I think it's here. This here both have the dirty there, so you need to pull that out. That's why the comment, must be divided and multiplied by the dt respectively. That's the reason why when I read this, E dot is supposed to be E minus OD and divided by dt, right? We didn't see that literally here, and this comment actually makes everything complete, because we actually, because this divided dt, 1 over dt or the small dt, they are constant when you pick this up. So you can put this into this constant combined with this ki and kd here, okay? That's certainly the comment about it. This actually is important, because if you just go through this, it looks weird, because right, E dot, just let me show you again. E dot, it should be like E new minus divided by t, right? Well, actually you don't see that here. So the way they take care of this is actually they say this thing KD and KO actually includes the sample time. So it must be divided. They must be divided in the case of KD, or multiplied by DT in the case of KI respectively. Okay. All right. And that's the summary. I would see we have covered the PID theory in detail, and we go through the implementation of PID controller on computer, and put what we have learned to control cruise, certainly the speed of a car. Now here the question I ask is, how do we put this into control of robotic manipulator, right? You have the car, and we remember, as I said, actually, you to answer this question, essentially you need to think about your problem at hand, compare them side by side, right? For example, you for the velocity, sorry, for the cruise control case, you have the velocity of the car as a state variable, and you have still the velocity of the car as the output, which you can measure, right? And what else? then you look at the robotic manipulator case. Are you trying to are you trying to are you trying to achieve some constant speed, or are you trying to achieve some position, right? So depending on your case, well, obviously for robotic manipulator, pretty much it's more like the position, right? So you can put the position as the state variable. You can track it, and also you can measure, right, as outputs, same thing. And also you have a reference in a car case. You have a reference speed. Here you have a reference position, or which is your goal, right? The place you want to reach. So all these things, and eventually you will realize actually you need to look at the most difficult part. Actually, is the dynamics, because in a car case you have dynamics. It's certainly F equal to ma. You can write that down, right? But in the robotic manipulator case, it just seems more complicated, right? You don't have a single mass. It's not a single rigid body. Actually, it's we model the manipulator arm as a series of rigid links, obviously linked together by two types joints. One is a railroad and one is prismatic, right? So you have, but we have worked out the details of the dynamics, or for the robotic manipulator, and you have the dynamic equation actually. Yeah, dynamic equation that actually describes the position, how the position changes when you apply external forces. So that's what you need when you want to control a robotic arm. Okay, now here in this class, I think we don't have that much time to go through that in detail this time. Well, if you're interested, I would say just look at the homework 5, problem 1, right? You are asked to derive the dynamic equation, and you can. I'm pretty sure you're gonna find that out. And also in the last problem is the problem 4. I think it's problem 4. You are asked to do the dynamics of epidemic, right? So same thing. I mean, we write down the equations. If you treat this as a math problem, then everything is the same. If you treat this as a math problem, everything is the same. Okay, it doesn't matter whether it's epidemic, or a cruise control, or the temperature of your house, right? You have a small meter measuring thing, and then try to it's certainly your air conditioning system, or it's a robotic manipulator. It really doesn't matter. Okay, I hope by doing this and by going through this example in detail, you have the rough idea of what is going on with control, and you have some feeling about how this is done in reality, okay, in practice, in industry. Okay, that's the end of this lecture, I will say. I hope you still enjoy the last evening before the new week. I'll see you on Tuesday. When we'll distribute the robotic manipulators to the groups, and also we start looking at image analysis. Okay, and that's gonna be interesting, and you can see how as I said, the linear algebra stuff can be directly used there, just like you have been using for the robotic manipulator, the dynamics, the kinematics, and statics. Okay, I want to see this again. Everything is the same in the sense of mass. Okay, you can use. That's really why math is such a powerful tool. If you learn the math well, then you can use it to solve different problems. Okay, enough of stuff from me. I will say good night, everybody. I'll see you on Tuesday. I look forward to it.